Good day, everyone. Today we talk about logic families. Logic families are a class of devices who are characterized by specific ranges of temperature, specific ranges of voltage, speed, etc. Let us see the different types of logic families today. Bipolar and unipolar. Bipolar refers to those families or devices that are actually composed out of BJTs. ULF or unipolar devices are composed of CMOS devices. Now within BJT itself, there are saturated and non-saturated classes. In saturated, what happens is that the BJT is operated up to the saturation mode of operation. That is, it works between cutoff and saturation. But in non-saturated, what happens is that the BJT will not be allowed to go into saturation. It is actually working below saturation, that means in the active region. In case of unipolar logic family, CMOS or complementary MOSFETs involving MOSFETs. MOSFETs may be PMOS or NMOS, that is P-channel or N-channel MOSFETs. As the name suggests, P-channel meaning holes are the carriers and N-channel meaning electrons are the carriers. So in case of unipolar, only one of these types is the carrier, that is either holes or electrons. But in case of bipolar, as the name suggests, both holes as well as electrons are involved in the conduction. Within bipolar saturated itself, we have all these classes of logic families, RTL, DTL, TTL, etc. In non-saturated, you have Schottky and ECL. ECL is an important class, but ECL is used where high-speed applications are required. Where high speed is very important and other parameters are not can be sacrificed, we go for ECL. But in case it is not that important, we go for the other families. Okay. Complementary MOSFET actually involves both PMOS as well as NMOS in the same circuit. Okay. So those are the different types of logic families, and as I said, they are characterized by different parameters which we are going to study today. The classes of logic families are, the main ones are TTL, ECL and CMOS. TTL is transistor-transistor logic and it is made using BJTs, and the inputs are applied at the emitter of the BJTs, and if you have more than one input, it is applied as multi-emitter BJTs. In case of ECL, as the name suggests, the emitters of the transistors are connected all together. That is why it is called emitter-coupled logic family. And the transistors are operated in the active region or maybe up to the cutoff region. The inputs are single inputs, they are not multi-emitters. CMOS family consists of or uses MOSFETs, both NMOS as well as CMOS, PMOS are used, and they are constructed symmetrically and they complement each other because the advantages of both NMOS as well as PMOS are combined. Both advantages are combined. This is a comparison table of all the families that we just talked about right now: TTL, ECL, CMOS. These are the important classes of logic families. We will not understand these parameters right now when I say fan out, noise immunity, etc., which is the purpose of this video. We will be talking about each parameter and we will be explaining what each parameter means. Okay. As in the previous table, these are listed out. That is a logic, low voltage, high voltage, noise margin, propagation delay. All these parameters we will be familiarized with right now. Let us start. If you are given a data sheet of any device, if you have a device 741 AC or 7400 IC, or as you have here, you have a part here. This is the NAND gate, and you see when you open the data sheet, you see a lot of parameters, electrical parameters, and half of them you might not understand. So let us endeavor to understand the parameters that you see listed out in a data sheet. Okay. Because a data sheet is what you open in the first place when you want to use an IC. The first parameter would be the logic levels. Logic level refers to voltage logic levels as well as current. What do you mean by a logic high and a logic low? A logic high refers to a high voltage and a logic low, that is 0, refers to a low voltage. A high voltage in case of TTL logic family, a high voltage is actually 5 volt and the logic 0 is actually 0 volt. Now if I take any device, when you produce a logic 1, suppose it is a TTL family as we are talking about right now, the logic 1 would actually mean 5 volt and the circuit is perfectly capable of producing a perfect 5 volts. Since no other parameters, no other interferences are coming in between, the output is directly produced by the circuit and probed at the output point itself. So a perfect 5 volt is inevitably obtained. But if the same circuit producing the 5 volt, the same signal is transmitted over some channel or any medium, even if it be a long wire, it is transmitted and provided or applied at the input of another circuit, say circuit number 2. This 5 volt might get corrupted by noise. The noise interference comes in between. So as it comes and interferes with the signal, this 5 volt may get corrupted. So even though I need a logic 1 or I am expecting a logic 1 at the input of the new device, I may not get a perfect 5 volt. This 5 volt will be corrupted. Maybe I get a 4.5 volt or I get a 3 volt, and still the second circuit should recognize this voltage as a logic 1. How do I do that? How do I give allowance for this interference caused by noise? So this allowance is provided by allowing that the voltage at the input of the device can be less than 5 volts. It is allowed. You are making allowance for noise. You are making a margin for noise. That is, any voltage less than 5 volt may still be taken as logic 1. Now, you cannot make 100% allowance as in any voltage being taken as logic 1. Of course, that would not make sense. So what you do is you put a limit, a minimum value of say 2.5 volt. Any voltage less than 5 volt, but it should be greater than 2.5 volt, say, will be considered as a logic 1. And why are we talking about this margin? Because you have to make allowance for noise. So this margin, which makes allowance for noise or which tolerates noise, is referred to as noise margin. Since we are talking about logic 1, this is noise margin height. Okay, I hope you got the point. Right. Now, if I take logic 0, the story is in similar manner. If I take this first circuit here and the second circuit here, the circuit produces logic 0, which is a perfect 0 volt. So perfect logic 0, which is symbolized or which is designated by 0 volt, as it is transmitted over the channel, it gets affected by noise and it comes to the input of my second device. It may not be 0 volt, it may be a voltage greater than 0 volt, say 0.1 or 0.2, so on. Okay. So I have to make some allowance for noise, say up to 0.8 volt. That is a value for TTL. So up to 0.8 volt, 0 up to 0.8 volt is the allowance or the tolerance of noise in the case of TTL. So this margin which you have allowed because of noise is referred to as noise margin low. Now we have designations or we have notations for each of these voltages. The voltage produced at the output, okay, O stands for output, corresponding to logic high. Voltage V at the output O, corresponding to logic high H, is VOH. In this case, 5 volts. So this is my VOH. Okay. The voltage at the input VI, corresponding to logic high, is called VIH. And the minimum voltage for this is VIH minimum is 2.5 volt. VIH minimum is 2.5 volts. Okay. At the output, VOH is the minimum. That means you are expecting full 5 volts. So you will not compromise. You are expecting a full 5 volts. So VOH minimum. And at the input of the second circuit, you have VIH minimum, and that is equal to 2.5 volts. Similarly, you have notations for this also. That is, the voltage at the output is VOL. That is VOL is output corresponding to logic 0. and the voltage corresponding to logic 0 at the input is VIL. The maximum that is allowed is 0.8 volts, so I will call it VIL maximum. So corresponding to logic low or logic 0, it is maximum. So this is VOL maximum and this is VIL maximum. Okay. So this is the noise margin low and this is the noise margin high. Okay. So let me call this as NMH and this is NML. If I want to write an equation for NMH, I will write it as NMH is equal to this duration from VOH to VIH, isn't it? So I will write it as VOH minimum minus VIH minimum. Okay. The same way, NML is equal to VOL maximum minus VIL maximum. Okay. That is the difference between these two lines. So this is the equation for NMH, noise margin high, and this is the equation for NML, noise margin low. Okay. So shall we see this in a little more detail? The first thing we talked about was voltage levels, VOH minimum and VIH minimum. VOH minimum is a high level output voltage, that is a minimum voltage level that a logic gate will produce as a logic 1 output. And VIH minimum is a high level input voltage, that is a minimum voltage level that a logic gate will recognize as a logic 1. And below this level, you will not accept it. Like we talked about 2.5 volt, any voltage less than 2.5 volt is not accepted as a logic 1. Correct? The current corresponding to VOH, high level output current, is IOH. And the current corresponding to VIH is IIH, that is high level input current. Okay. As you can see here, this is the first gate and this is the second gate. Just like the circuits that I indicated just now. From the first gate, the output is VOH and the corresponding current is IOH. The input at the next gate is VIH corresponding to logic high. V voltage, I input, H high. And the current corresponding to it is I current, I input, H high. IIH. Okay. For a logic low or 0, the voltage at the output will be VOL. The maximum that is allowed is, in this case, it was 0 volt for TTL. So maximum voltage is VOL. There is a low level output voltage, that is maximum voltage level that a gate can produce as a logic 0 voltage. What about VIL maximum? Low level input voltage, that's the maximum voltage level that a logic gate will recognize as logic 0 input. Okay. Above this value will not be accepted. Like we talked about 0.8 volt in case of TTL, remember? Yes, above this value is not accepted as a logic 0. The current corresponding to VOL, that is a low level output current, is IOL. Current corresponding to VIL is IIL, that is a low level input current. Okay. From the circuit, once again, this is 1 and this is 2. And the output of this first circuit is VOL, corresponding current is IOL, because for the one that you're producing, the logic that you're producing is 0. The same 0 reaches the input of the second gate, that is the inverter in this case, that is logic 0. The voltage corresponding to it is VIL, V voltage, I input, and L logic low. The current corresponding it is IIL. Okay. The ranges that we talked about earlier, that is TTL, the voltage is 5 volt and 0 volt. And between 0.8 and 2.5 is not defined. That is why it is referred to as indeterminate. Let us hope that the circuit does not go into this voltage range, because if it does go into that voltage range, the gates will not be able to, or the modules will not be able to determine whether it is 0 or 1. That is why it is called indeterminate. In case of CMOS, of course, it depends on the supply voltage. If the supply voltage is 5 volt, 3.5 is the minimum voltage that will be taken as high. And the maximum voltage that will be taken as low is 1.5 volt, maximum voltage. Okay. This is VOH minimum and this is VOL max. Okay. Of course, VOH and VOL are the voltages that we are producing for logic high and logic low. Therefore, it has to be perfect. There is no noise expected. and therefore it will be a perfect 5 and a 0, that is according to the supply that we are giving. Noise margin is what we have explained earlier. If you have the first circuit here and the second circuit here, there will be noise interference between these two, and because of this noise you have to make allowance for this margin. Okay, so NMH is VOH minimum minus VIH minimum. Similarly, what about this? NML is equal to VIL maximum minus VOL maximum. Okay, so these are the equations for noise margin. Okay, the equations as we saw right now. Typically, VOH, the output high, is VDD. In case of TTL, what was VDD or the supply? In case of TTL, the supply was equal to 5 volt. And VOL is equal to ground. In case of TTL, that was equal to 0 volt. This is an example. So if you are asked to calculate the noise margin of a 7/4 LS series, usually 7/4 series are all TTL. Okay, these parameters are all given to you, and that is VIH, VIL, VOH, VOL are all given to you. You are expected to calculate the noise margin. So noise margin you have to calculate NMH as well as NML. We already know the equation for NMH and NML. What is NMH? That is noise margin high. Okay, that is equal to VOH minus VIH minimum. And the values that are given are 2.7 and 2, therefore you get 0.7. Similarly, NML corresponding to low is equal to VIL minus VOL, that is 0.8 minus 0.4, that is equal to 0.4. Noise margin is a quantitative measure because you can actually have a specific value for noise margin high and noise margin low. Now, from the specific value, the quality of having resistance to noise or tolerance of noise, that quality is referred to as noise immunity. Okay, so how much noise immunity do you have is referred to as noise margin, and if you have more immunity to noise, that is noise immunity. If you have less immunity, that is characterized by the term noise immunity. Your tolerance to noise is more or less. That is characterized by noise immunity. But if you want to know how much tolerance you have to noise, that is characterized by noise margin. Okay.